want to experience what an F1 driver
from A to the reference node, we are using nodal analysis. Now nodes are A, B, and this is the third node. Say this third node is the reference node. C is the third node. Between A and C, we have say this branch with 2 ohm, then in series with 6 ohm, and across the 6 ohm resistance, the voltage drop is considered to be V1, and this dependent source is 3V1. That means, what is the value of V1? Here the voltage is VA with respect to node C, then V1 will be VA acting as potential divider. VA divided by this total impedance will be the current flowing through this path multiplied by 6. That means
by 8.
6 VA by 8 is the value of V1. Okay, remember this. V will be 6 VA by 8. Okay, V1 is. Now, for this circuit, we can write that matrix vector, that equation we can write that Y into V equal to I. This is the admittance matrix multiplied by the voltage vector equal to injected current, and the admittance matrix for node A, you see that 1/10 because of this branch, 1/38, then because of this branch it will be 2 plus 6 8 1/8 plus 1 1/48 because this node is B. We have given a different name here B, and B is a variable. Okay, so self admittance of this node is this thing. Mutual admittance between node A and B, 40 ohm is the resistance, so minus 1/40 is the mutual admittance between node A and node B. Okay. Similarly, between node B and node A, minus 40 will be the admittance. For node B, what is the self admittance? It is the this admittance plus this admittance. That means 148 plus 112. Okay, this is the summation is admittance of node B. So self admittance of node B, self admittance of node A, mutual admittance between node A and B, mutual admittance between node B and A here. Okay, this is multiplied by VA, VB, the node voltages, and injected current. For node A, how much is the injected current? This is 0.55 volt is the voltage. So because of this 0.55 volt source, what will be the injected current? It will be, you see that if we convert it into a current, 55 by 10 is the current, so injected current here. Similarly, for node B, what is the injected current? Here, voltage source is 3V1. It is positive terminal here. So if you consider this to be, that means you convert it as a current source, it will be 3V1 by 12 outgoing from the node because of positive polarity here and negative polarity here. So minus 3V1 by 12. Okay, it's clear. This current source where it is 0.5 by 10, and at node B where it is minus 3V1 by 12. Is it clear? Any question? Anybody? Any doubt? Can you follow this? Anybody who could not understand this?
স্যার একবার কারেন্ট সোর্সটা রিপিট করবেন?
Current source কি হবে? For node A, what is the injected current source or injected current at node A due to the voltage or current source, whatever may be here. We have a voltage source here. So if you consider this voltage source, how much will be the current injected here? You convert this as a current source. It will be 0.5 by 10 will be the current source value. Current source, that means arrowhead will be towards node A. That means current value will be 0.5 by 5 by 10. Current is injected into the node, therefore it is a positive polar, positive source. Now for node B, there is a between node B and the reference, we have the resistance 12 ohm in series with the source 3V1, dependent source 3V1, with positive terminal here to at the end C and negative terminal here. Okay, so if we convert this into a current source, how much will be the current entering into the node? It will be a current source, then it will be 3V1 by 12. That means voltage divided by series impedance will be the current source value. Okay, 3V1 by 12, and arrowhead of this current source will be at the positive terminal here. That means at C. That means this current is going out of node B. So injected current is positive, current going out will be negative. So minus 3V1 by 12. All right.
Okay, sir.
Now you see that if you see this part of the matrix, now it is a symmetric matrix. Okay, but obviously the equation that we have written, not in the, this is not in the final form. We cannot solve this equation now. Why? Because the variable is 3V1 by 12 is on the right hand side, which we have to move it towards the left hand side. Okay, right hand side has to be constant. So if you move 3V1 by 12 on the left hand side, what will be the equation? What is V1? V1 is, as I have seen, V1 is 6 VA by 8. Okay, from this V1 is 6 VA by 8. That means 6 VA by 8. You can put in place of V1, you can put 6 VA by 8 like this. V1 equal to 6 VA by 8. Okay, so if it is 6 VA by 8, then it is 3 by 12. Now this 3 into 6 VA by 12 into 8. This will be moved to the left hand side. That means this, if you move this to the left hand side, where it will be added up? Here it will be added up. It will be minus 40. Then this part will come here. It will be 3 into 6. Then 12 into 8 here. Okay. So this will be the modification in the admittance matrix. Am I clear? That means if you move the variable part, that means the term involving the variable, if you move it to the left hand side, then you see that it is no longer minus 140. It will be changed to some other value. 3 by 12 into V1. V1 means 6 VA by 8. Then you move this part to the left hand side. That means it will be added up with this value. So now this is Y matrix, Y12 and Y21. They are not equal. That means this matrix, the final form of this matrix, if you write this, you see that this matrix is no longer symmetrical. Okay. Is it clear? Is it clear? Any question, anybody?
Sir, can you explain it once more?
Now, this equation, is it clear to you? Whatever is written now, that self-admittance, mutual admittance, self-admittance into voltage variables equal to injected current. Is it clear?
Yes, sir.
Now, can you solve it now directly?
No, sir, because
No,
three variables.
because the variable is on the right hand side. So to change the variable or shift the variable from the right hand side to the left hand side, if you shift it to the left hand side, where this 3V1 by 12 with a negative sign minus 3V1 by 12 will go, it will be added up where? It will be minus 3V1 by 12 means minus 40 into VA plus 1 upon 12 plus 1 upon 40 into VB equal to minus 3V1 by 12. This is the full equation. Okay. If I expand it, it will be minus VA by 40 plus VB into 1 upon 12 plus 1 upon 40. That is equal to minus 3V1 by 12. Now what is V1? V1 is 6 VA by 8. 6 VA by 8. You put the value of V1 equal to 6 VA by 8 and rearrange the equation. Okay. Then what will be the form of the equation? It will be minus 1 upon 40. Then this come here, it will plus 3 into 6 by 12 into 8. Okay. VA was there. Then here it will be 112 plus 140. Then here it will be 0. This will go to the left hand side, and 3V1 by 12 with the negative sign, this will become 0.
Okay,
This
sir.
is the
Okay.
equation. Okay. If this is the equation, you see that now this part has been changed. This is changed now. It is no longer minus 140. You have plus 3 into 6 divided by 12 into 8. That means now the admittance matrix is no longer symmetric. Okay. It is Y11, Y12, Y21, Y22. Y12, Y21 previously was same. Now Y12 and Y21 are becoming different. That means the matrix is no longer symmetric. All right. Now why the matrix is no longer symmetric? Who is responsible for that? Previously, whenever we have written, always we had the symmetric matrix. Okay. Here you see that Z12 equal to Z21, Z13 equal to Z31, Z23 equal to Z32. It was there. Now in this circuit, Y12 and Y21, they are becoming different. After this modification, it will become different.
এটা কি ডিপেন্ডেন্ট সোর্সের জন্য
Independent voltage source.
Because of the appearance of the dependent source. Okay, that means you can say that this dependent source is making the matrix asymmetric. Okay, that means that this admittance matrix is becoming asymmetric. This is due to the presence of this dependent source. That means in presence of dependent source, see that now what has happened, the admittance matrix has become asymmetric. Okay, is it clear? So later on we shall see that sometimes because of the presence of this dependent sources, admittance matrix will become asymmetric, but some other times it may remain in symmetric condition. That also we shall see. But we can say that is asymmetric. This is due to the presence of the dependent source. Okay, at what condition? The presence of dependent source in the admittance matrix in the work will not make the matrix asymmetric. That we will see later on. But for the time being, we see that because of the incorporation of this dependent source, the admittance matrix is becoming asymmetric. So admittance matrix or the impedance matrix, that means the network matrix, may become asymmetric because of the presence of the dependent source. Okay, this is our learning from here. Is it clear? Now once you can write this, obviously you can solve. You can solve for VA, you can solve for VB, no matter. Very simple. You can write the matrix, you can solve it. Is it clear?
Yes, sir.
Okay. Next, we shall have to consider more examples so that everything becomes clear here. Now again, we are considering example of voltage source without series resistance and current source without parallel resistance. How to convert from one source to another? We have done it already, but let us now take some more examples. Here we have it's very simple network. Okay, with a very simple with only the resistances. There are 4 resistances connected in this fashion, 1 voltage source and 1 current source. Okay, now let us convert these voltage source into current sources. Directly it is not possible because there is no resistance connected in series with this source. Okay, directly no resistance is connected with this 3-volt source, but we can do. Previously also we have done. Let us do it again. Okay, if you represent this source, 3-volt source, in this fashion as in figure 9.2, that means as before, a single 3-volt source is replaced by, or it is represented by, two 3-volt sources in parallel. Okay. Now you see that it is node D. It is node D. We have joined this through another wire, you can say, but it remains D because they are potentially same. They are connected. So this is also D. Okay. Now what we can do from this figure 9.2, it may obtain figure 9.3, where since they are in the same potential, let us remove this short circuit. Okay, I am drawing this to explain it further. If you remove this, what is the change? Simply between 9.2 and 9.3, between these two figures, only change is that this short circuit between these 2 points, which are actually identical point, we have separated them for convenience. Between these two terminals, there was a short circuit path. Now that has been removed, but removing this short circuit does not change any condition, any operating condition of the network, because voltage remains as before, current remains as before. Okay, so easily you can do that, because without any disturbance to the network, we can simply remove this short circuit, and we have removed it from here. Okay, if you remove it from here, now you have 3-volt source with 3 ohm in series, 3-volt source with 1 ohm in series. Okay, easily you can convert this voltage source into current source. This voltage source also is a current source. So between C and B, there will be a current source. Between A and B, again there will be a current source. That has been done in figure 9.4. Okay, between A and B, we have this 2 ohm resistance, and to represent this 3-volt in series with 1, we shall have 3 ampere in parallel with 1. So it will be 3 ampere injected into the node in parallel with 1 ohm resistance injected. This current source is injected toward node A because the positive sign here is near at the end A. That's why. Similarly, between node C and this reference node B, we can have this current source to represent this voltage source. 3 volt in series with 3 ohm resistance will be represented as a 1 ampere with 3 ohm in parallel. Okay, 1 ampere in parallel with 3, and already there was a current source of 2 ampere that was there. Okay, now you have the final network like this. For this network, now you can write the nodal equation. Okay, if you write the nodal equation, what will be the self admittance of this node? It will be 1 plus half plus. This was how much? Between A and C, this was 4. Okay, 1 plus half plus 4. Between A and C, this is 4 ohm. Actually, that was a mistake that I have not written it here. So 4 ohm. So minus 1/4 will be the mutual admittance. Between C and A, again it is minus 1/4. And at node C, this is 1/4 plus 1/3. 1/4 plus 1/3 is the self admittance. VA, VC as the variables, and injected current at node A, it is 3 ampere is the injected current. At node C, it is 2 plus 1, again 3 ampere. Okay, so this is how we can write the nodal equation. Okay, that means for writing nodal equation, we had voltage source. We could not write KCL, that means could not form admittance nodal equation directly. So that's why we had to convert this 3-volt source into current sources, and this is how it had been converted, and finally we have written this equation. Once you can write this equation, now you can solve. Okay, if we will solve this, I will get the result, no problem. Is it clear how we have done this? How 3-volt source has been converted into current sources? And finally, we have written the nodal equation. Any question here? Any doubt here? Anybody? Any question? Everybody could understand?
Yes, sir.
Okay. Then if you We've understood this. Now let us do the other way. Now therefore, say retaining this 3-volt source, let us convert this current source into voltage source or voltage sources. For the current source also, the problem is same. You see that if a current source has to be converted into a voltage source, there must be some resistance in parallel or must be some impedance in parallel with the source. In this case, there is no impedance directly connected across the current source because current source is connected between node C and B, and resistances are connected between node C and A, and then between A and B. Not direct connection is there. Okay, but we can convert this source into voltage sources. Okay, how? What you can do? You for this network, what you can do? There was a source here. Uh, this was source here. So I shall connect from B to A. 2 ampere source will be shown, and from A to C again 2 ampere source will be shown. Actually, the source is connected between B and C and directed toward C. What I can show, as if this same source is connected from B injected to A, and then from again coming out from A, it has been connected to C. So effectively the situation remains same because previously here there was no current source connected at node A. Now two sources are connected at node A. One is entering into the node at node A, another is leaving the node. So that means at node A, effectively no source is connected. One has entered and it is left finally. So effectively no change. But under this process, what we have done, we could connect a current source in parallel with a resistance, this current source in parallel with this resistance. Now this combination 2 ampere with 2 ohm in parallel may be converted into a voltage source here, 4 volt with 2 ohm in series. 2 ampere in parallel with 4 ohm may be converted into a voltage source again, 8 volt in series with 4 ohm. Okay, now you see that now the network become like this. Obviously, because of this source conversion, there will be some changes in the network. Okay, some of the branches, some of the nodes may disappear. Okay, therefore, while applying this source transformation, you have to do it very carefully, whether you are losing any node or any branch which is actually required for you. That you have to check this, and therefore applying source transformation has to be done judiciously. Okay, in this case, what we have done after this transformation, we are obtaining basically two loop, one here and here, and now we shall be writing loop equation. That means we shall be solving the network using loop analysis technique. Previously we have solved it using the nodal analysis technique. Now for writing loop equation, for this is loop A and this is loop B, self impedance of loop 1 here is 1 plus 2, that means 3 ohm. Mutual impedance between 1 and loop 2 is, this is the mutual common, minus 1 ohm. Then between 2 and 1, this is common, minus 1 ohm. And the self impedance of the second loop, 3 plus 4 plus 1. These are the resistances in loop 2. So 3, 4, 7 plus 1, 8 is the self impedance of loop 2. I1, I2 are the loop currents. And what are the sources in loop 1? 3 volt source, and we have 4 volt source here. 3 volt source with a positive terminal here and negative terminal here means that natural current of this source will be outgoing from terminal positive. Natural current of this 4 volt source will be going out from this positive terminal. That means you can say that 4 volt source at loop 1 will be a negative source, 3 volt source at loop 1 will be a positive source. That's why 3 minus 4. Similarly, for the second loop, we have 8 volt source. Okay, here this is the direction of current clockwise, I2. I2 you see that is entering through the positive terminal, but natural current of this 8 volt source should go out of the positive terminal. So they are opposing each other. Therefore, 8 volt will be a negative source here, and it has become negative. Okay, so now this is how we can convert a current source into two voltage sources and finally can write loop equation. Okay, Is it clear? You see, conversion of voltage source to current sources and current source to voltage sources, and finally how we have written loop equation and nodal equation.
Sir, can you explain the step from 9.2 to 9.3 to 9.4 once again? The previous one.
9.3 to here to here.
9.3 to 9.4.
9.3 to 9.4. Okay. Here you are where here we are actually writing the nodal equation. Okay. Now is this 9.3 clear? From 9.2 it is clear.
Yes, sir.
9.2 to 9.3 is clear. Now at 9.3 you see that between C and D, within these two nodes, we have this 3 ohm resistance with series impedance 3 volts. So this combination can be converted into a current source of 3 volt by 3 ohm, means 1 ohm connected between B and C, entering towards C, and 3 ohm will be in parallel connected between C and B. So here you see that between C and B, this is B means this is also B. We have 3 ohm connected between C and B, and here 3 volts by 3 ohm means 1 ampere. This is 1 ampere source entering into node C because of this source. Is it clear? For this branch, this conversion is clear that this is the branch and this is their impedance. Okay.
Yes, sir.
Now between A and B, there is another voltage source with series impedance between A and B. 3 volts in series with 1 ohm. If we convert it into current source value will be 3 volt divided by 1 means 3 ampere connected between B and A, 3 ampere connected between B and A and entering towards A. Okay. This 1 ohm will be in parallel between A and B. Between A and B it is connected, and 2 ohm was already there. So from this figure where we had voltage sources, we have converted all these sources into current sources, and this is the final figure. Is it clear now?
Yes, sir.
Okay. So once this is clear, I think this matrix, nodal admittance matrix is, you can follow this, or shall I explain it?
No,
further?
sir, it's okay.
Okay. Now here we had a current source. What the current source was? It was between this node and this node. If you see the original figure, between this node and between B and C. But with the current source between B and C, we want to write the nodal loop equation now. For writing the loop equation, you have to write the KVL equation. For KVL equation, you write basically the voltage drop and voltage source in terms of these things. You write the equation. Okay. So since we have a current source, we have to convert into a voltage source now. For that, we actually needed a resistance, or there's an impedance connected between node B and C that is not there. So directly we cannot convert this 2 ampere current source into a voltage source. But what we can do? We can show that as if these 2 ampere source is first connected from B entering into node A, and then it is leaving node A entering into C. So if we draw this in this way, effectively the current at the nodes remains unchanged. So that has been done here. That has been done here. From it is from here B to A, and then A to C. At node A, there was no current source connected. Now there are 2 current source connected. One is entering 2 ampere, another is 2 ampere leaving, means effective current source connected at node A is as before, it remains 0. Okay. So now if you have a current source like this with parallel impedance, this may be converted into a voltage source with series impedance. Again, this current source with parallel impedance may be converted into voltage source into series impedance, into source in series with series impedance. Therefore, now this circuit, figure 9.5, can be transformed into figure 9.6. Now we have two loops, and for these two loops, very simple loops are there. Obviously, we can write the loop equation. Is there any doubt, any question for this figure 9.5, 9.6, and the following?
স্যার 9.6 এ আপনি যে দুটো লুপ নিয়েছেন তার অন্য যদি আমি একটা লুপ নিই মানে বড় সার্কিটটা পুরো লুপটা যদি নিই তাহলে কি একই ম্যাট্রিক্স থাকবে?
বড় সার্কিটটা মানে তুমি বলতে চাইছো
মানে
যে
হ্যাঁ
এইভাবে লুপটা লিখবে তো না, ইকুয়েশন পাল্টে যাবে, তখন একই থাকবে না তো।
মানে ম্যাট্রিক্সটা একই থাকবে না, মানে যেটা
ম্যাট্রিক্স তো একই থাকবে না, কি করে থাকবে? কারণ লুপের পাথের ইম্পিডেন্স তো চেঞ্জ করে যাচ্ছে, কাজে লুপ একই থাকবে কি করে? লুপ ইকুয়েশন উইল বি অ্যাজ ইউ সিলেক্ট দ্য লুপ। আমাদের কি করতে হবে? এমন ভাবে সিলেক্ট করতে হবে যাতে all the branches are included in one sum of the loop, যাতে ঢুকে যায়, কেউ যেন বাদ না পড়ে যায়। এখানে আমরা দুখানা সিম্পলেস্ট ফর্মের লুপ যা পেয়েছি সেই দুখানা সিলেক্ট করেছি, যার জন্য লুপ ইকুয়েশন লিখেছি। ওকে,
আচ্ছা
obviously I could write differently also. So I could write this, say I2 remaining same, I this, and this loop could have been like this, এরকম দুখানা ইনক্লুড করে করতে পারতাম, করা যেতেই পারতো, তাতে কোনো ভুল নেই। কিন্তু ইন দ্যাট কেস অবভিয়াসলি ইকুয়েশন উইল বি সামওয়াট ডিফারেন্ট, তাই না? কারণ সেই কারেন্ট, এই লুপ কারেন্ট I1 আর আমি যদি ওইভাবে লুপ কারেন্ট দেখাই, এই দুখানা তো এক হচ্ছে না, আলাদা হচ্ছে, বুঝতে পেরেছো? অলরাইট, ইকুয়েশন আলাদা হবে কারণ না এলিমেন্ট গুলো আলাদা, তারপরে কি দাঁড়াবে সেটা আমাদের দেখতে হবে, ঠিক আছে?
ইয়েস স্যার।
How you form the loop, accordingly the equation will be changed. Okay, তাহলে এইভাবে আমাদের এখানে দেখানোর উদ্দেশ্য ছিল যে ইভেন ইফ a voltage source is not having series impedance, we can convert the voltage source into current source. Even if a current source is not having a parallel impedance, that source can be converted into one or more voltage sources, and we can write the equation as required. তাহলে ইকুয়েশন যেটা লিখতে চাই সেটা আমরা লিখতে পাচ্ছি, কিন্তু আমাকে দরকার মতো সার্কিটের সেই মডিফিকেশন, সেই ট্রান্সফরমেশন গুলো করে নিতে হবে। কি করলে কি হবে সেটা ডিপেন্ডিং অন দ্য সার্কিট, ইউ হ্যাভ টু ডিসাইড। ইজ ইট ক্লিয়ার?
Yes, sir.
Okay. Yes. Now it's the same thing. I'm proceeding slowly. Now let us consider the same circuit. Same structure remains same, but whatever we have done here, we have simply changed the sum of the source. That means this is the current source here. It was an independent source. Now we have shown it as if this source is dependent. Instead of showing the independent source here, I am now showing a dependent source here to show the effect of dependent source. Already this has been discussed, but again we are showing that what happens if a dependent source is actually included in the circuit. So how the transformation has been done, you have seen. So in the same process, you can convert this current source, dependent current source, into voltage sources, and finally you can write the loop. Okay, just the previous step we have done this. So obviously I think there is no problem in following this. Same thing, simply the current source, which was of say a 2 ampere current source, now is being shown to be a current source of 2I2. What is I2? I2 is the current through this 3 ohm resistance branch. Okay, তাহলে এইবার আমরা এরকম একটা সোর্স ইকুয়েশন, এরকম একটা network পেলাম, and then it has been converted into this network of figure 10.3, where again we have two loops. We have voltage source here, independent voltage source, and dependent voltage source. Here we have the dependent voltage source. Previously it was independent. Okay, now you write the equation in the same fashion. You can write the impedance matrix, loop current vector equal to injected current. Sorry, loop impedance matrix into current equal to loop voltages. Loop impedance, loop current, and then loop voltage. So in loop 1, I am displaying the right hand side because this part remaining same, it's same as before. Okay, In loop 1, 3 volt is the independent source, voltage source, and 4i2 is the dependent voltage source. You see that 4i2 will appear as a negative source here because direction of I1 and the natural current due to 4i2, they are opposite, in the opposite direction. This is the direction of current I1, and this source should deliver a current from the positive terminal to the outside network. So since they are in opposite direction, the effective source in the loop will be 3 minus 4i2. Here in this figure, in the second loop, this is the direction of current of the second loop, the clockwise current I2. But the 8i2, this source will deliver a current which is leaving the source through its positive terminal. That means it is opposing I2. Therefore, this 8i2 also will be negative. When this 8i2 is there and minus 4i2 is there, you see I2 and this I2. What effectively is I2? I2 is the current through this 3 ohm resistance. Okay. Means this I2 is nothing but, we can say this same I2 is loop current I2 is same because through this resistance it is I2. If you consider the loop current to be like this also becomes I2. So this is a variable to be shifted on the left hand side. This is also variable has to be shifted on the left hand side. So if you shift it, the equation is changed to this one. 3 minus 1 16 I1 I2 equal to 3 with 0 is the value in the right hand side. Okay. Now you see that this impedance matrix, this is impedance matrix into current vector equal to voltage. This impedance matrix again has become asymmetric because this 3 here we have minus 1 here. That means the final form of the loop impedance matrix is no longer symmetric, and this is due to the appearance of the dependent source. Previously, when we have shown the independent source, it was symmetric, minus 1, minus 1. It was a symmetric matrix. Now, with the dependent source, okay, dependent voltage source, now it is no longer symmetric. That means presence of dependent source makes the network matrix asymmetric. You can say this. Am I clear?
Can you repeat the step from upper matrix to the lower one? So can you repeat the step from that upper line, upper matrix to the lower one? That
to the lower upper matrix, this one.
Yes.
When we have obtained this matrix, when the source was independent source. Okay, the same steps we have followed. From this current source, we have converted into voltage sources and written the loop equation. Okay. So because of this, that means basically because of this circuit that has been transformed into this form, and finally we have obtained this form. That means because when the independent sources are present in the circuit, and we have converted the circuit, transformed the circuit to this final form, then the final impedance matrix network equation involving impedance matrix into loop current equal to voltage, that impedance matrix was a symmetric matrix. Why it was a symmetric matrix? Because Z12 and Z21 were they're as same. Z12 and Z21 they are same. Okay, means that this is a symmetric matrix. Now the same circuit, you see that now only the source has been, type of the source has been changed. It was a current source of 2 ampere value. Now it is a current source of 2i2, where i2 is the current through this 3 ohm resistance branch. Okay, that means a dependent source has been included in place of an independent source. And we have done the source transformation as before. We have written the loop equation, and we have written the final form of loop equation. The final form of loop equation, you see that this equation and this equation, what is the fundamental difference? Values are different, okay, but at the same time, property of the matrix, property of this matrix and this matrix are not same. this one is a symmetric matrix, but this one is an asymmetric matrix. Okay, but why this change has taken place? That has taken place because we have changed an independent source to a dependent source. That means we can say that presence of dependent source makes the network matrix asymmetric. Okay, presence of dependent source makes the network matrix symmetric. Can I say this? Is it clear?
Yes, sir.
Everybody, it is clear?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
All right. Then this is an example. I think I need not explain this. Just with somewhat more complicacy is shown here actually in figure 10.4. All right. Here you see that this is an independent source. I1 is an independent source. You consider that as if I1 is a known quantity because value is numerical value is not given, but as if I1 is a known quantity, I2 also is a known quantity. The quantity value is, I say I2, value is I1. So these are independent sources. As now there are dependent sources as well. 2V1 here between these two nodes. 3V1 a current source. 2V1 is a voltage source. What is V1? V1 is the voltage between this node and this node. We have an impedance of 1/4, and here the voltage is V1. That means if you consider this as a node and if you take this as a reference node, say it is node A, it is node B, and it is node C, then you can see that V1 is nothing but VA, voltage of this node with respect to reference. Okay, so it is VA. So according then this current source is dependent upon this voltage. This voltage source is dependent upon this voltage. Okay, now again you can transform sources and write loop equation. Write the ultimately we have converting into current sources and write the nodal equation. Okay, nodal equation, and finally you can obtain this final form figure 10.6. Okay, 10.6 you can obtain. Then you see that this is the final form. Here again Z1 sorry Y12 and Y21 they have become unequal, means again the network, because of this network where there are dependent sources, the admittance matrix became asymmetric. Okay, I am not discussing all the steps of this network because since I have explained the other circuits, I think you can very easily follow this circuit figure 10.4. You can easily follow. So you try it. If you face any problem in understanding, then I shall again repeat it. No problem. But I hope there will be no problem because steps are very simple. But only thing to be noted here is that here, because of the presence of dependent sources, finally the admittance becomes asymmetric. That means presence of dependent sources is making the admittance matrix asymmetric. Previously we have seen that while writing the loop equation, presence of dependent sources made the impedance matrix asymmetric. Now it is making the admittance matrix asymmetric, means presence of dependent sources may make the network matrices asymmetric. Okay, is it clear?
Yes, sir.
Yeah, and I have not discussed this all the steps of this circuit because you try it. There will not be any problem. If anybody finds any problem in understanding, indicate this. Tell me in the next class. I shall explain it again. No problem. All right. Okay. Now let us move towards the next topic. That is somewhat more complicated situation now. Gradually, level of complicacy will be increased. Okay. Now consider the situation where we will be discussing the so-called super node and super mesh. Super node. We know about node we know about mesh. Okay. Now a supernode. What is a supernode? Supernode means actually more than one nodes are considered, or they are behaving as a single node. Okay, more than one nodes are behaving as a single node, and we are considering them as a single node. Similarly, super mesh means more than one mesh are included in a single mesh. Okay, that means in a loop there are more than one loops. In a node there are more than one node, and those nodes are called supernode. Those meshes are called super mesh. Okay, let us again take the help of an example because it will be easier to understand with the help of example. Say we are considering this network, figure 11.1, page 11, figure 11.1. Okay, what is the network? Network is not very large. It is a simple network of 1, 2, 3, 4 nodes. Okay, 4 nodes, and we have a voltage source of 50 volt connected between node 1 and node 4, with node 1 terminal to be positive, node 4 terminal to be negative, 40 ohm resistance connected between node 1 and node 4, but it is connected in parallel with the source. That means you see that here this whole this source you cannot convert into current source directly. Okay, it is not possible. Something else has to be done. Similarly, between node 1 and node 2, there is a resistance of 5 ohm value. Current flowing through this branch, 5 ohm branch, it is marked to be I phi, as if whatever is the current flowing in this direction, that will be called I phi. We have given a name is given here. Okay, between node 2 and node 4, this is the resistance, 50 ohm is connected. Between node 2 and node 3, we have a dependent voltage source of 10 I phi. Okay, why this I phi is given here? Because a dependent source is shown between node 2 and node 3, where the source value is 10 I phi being the current flowing through this 5 ohm resistance branch and towards from node 2 to node 1. Okay, at node 3 we have a 4 ohm 4 ohm current source connected between node 3 and node 4, and in parallel this 4 ohm source, 100 ohm is the resistance connected. Okay, now we have to write nodal equation for this network. We have to solve this network using nodal analysis technique. So what we can do? We can write equation at node 2 and at node 3. It is node 2 and node 3, and for node 1 we are not writing any equation. Why we are not writing any equation? Because you see that if you are interested about the node voltages, for node 1 the solution is already known. For node 1 solution is known because the voltage is 50. Okay, so you know the voltage at node 1, the solution for node 1 is 50 volt. That's why we need not write any extra equation for that. Okay, but we have to know the equation for node 2 because the solution for this node voltage is required. Solution for this node 3 voltage is required. Let us assume that node 4 is the reference node. Okay. Now for node 2, if you write the equation, what will be the equation? Say here the voltage is V2, say this voltage is V1, it is 50 volt, but still let us write V1 to indicate this variable. Okay, V1 value is 50 volt, but let us write V1. So V2 minus V1 divided by 5, this is the outgoing current from this node, plus V2 by 50, that means current flowing through this branch. V2 is the voltage with respect to node 4. Obviously, we are assuming that V2 is at higher potential with respect to node 4. So, through this branch, current will be flowing from node 2 to node 4. So, V2 by 50 is the outgoing current. And through this, there is a voltage source connected. Between node 2 and node 3, simply a voltage source is connected. No series resistance is there. So, series impedance is there. Let us assume that through this source, the current that will be flowing is I ampere from node 2 to node 3. That's why we have written plus I equal to 0. So for node 2, equation 1 has been written. This is the current flowing outgoing from node 2 through 5 ohm resistance. This is the current V2 by 50 is the current outgoing from node 2 through this branch 50 ohm, and through this voltage source, dependent voltage source, we are assuming that the current flowing from node 2 to node 3 is I amperes. So summation of this 3 current 1, 2, 3 current is equal to 0 is the first equation. Is it clear? The first equation that I have written, we are assuming that I ampere is the current through the voltage source, independent voltage source between node 2 and node 3. Okay, we cannot write any current expression for that branch because there is simply voltage source is given. How to write the current expression? So that's why you are assuming current I to be flowing here. All right. Is it clear? Any doubt regarding this equation?
No, sir.
Now you write the equation for node 3. Same nodal equation, current KCL basically, we should write for node 3. Here at node 3, V3 by 100 is the current flowing from node 3 to the reference node. Okay, V3 by 100 outgoing current taken to be positive. Now we have assumed that through this 10 through this dependent voltage source, current is I ampere from node 2 to node 3. So this is I ampere is entering into node 3. That's why it is minus I. And 4 ampere source, it is delivering current 4 ampere into node 3. That's why it is entering current considered to be minus. So equal to 0. So equation for node 2 is written. Equation for node 3 is also written. All right. Now let us combine these two equations, 1 and 2. Okay. When we combine these two equations, what we can do? Our variables are say V1, V2, I. Here, okay, V1, V2, and I. Now what we can do? We can replace I from one equation to the other. Okay, we can replace I from one equation to the other. Here, V1, V2, V3, and I. There are 4 variables, obviously. 4 variables out of these 3. V1 is known, so 2 equations and 3 variables. Okay, obviously we cannot solve, but we know we require the nodal voltages. Therefore, let us replace I from this equation to that equation. So combining this, we can write this equation. Note equation 3 can be written. Okay. Now, what is equation 3? Now, match this equation 3 with this circuit of figure 11.1. It is at node 2, V2 minus V1 by 5, outgoing from node 2 through 5 ohm resistance. V2 by 50, outgoing from node 2 through branch 50 ohm. Then this is not there. Now then V3 by 100, V3 by 100, then minus 4. We have written one equation. Okay, whenever we have combined these two, actually what has come out as a result? As a result, we have obtained this equation, equation number 3, where you see that basically we have written the KCL equation combining this node 2 and node 3. That means as if we have considered node 2 and node 3 as a single node. Node 2 and node 3, they are 2 separate nodes. Okay, but as if the KCL equation is written, okay, for these 2 nodes taken together. How? We are considering current flowing through this, current flowing through this, current flowing through this, and current flowing through this, and as if 2 and 3 are being considered as a single node. This is a larger node. That's why it is called super node. Okay, when more than one nodes are considered as single node, they can be considered as single node here. Okay, they have been considered as single node, then it becomes a super node. We have written two equations initially, then combined those two equations and finally obtain this equation. And this equation is appearing as if we have written the KCL equation of this circuit for node 2 and 3, considering them to be a single node. While writing this equation, we have added up this portion with this portion. This is for node 2 and this part is for node 3, but we have written the same expression. Okay, that means these two nodes are being considered as a single node. And when this can be done, you see that this has become possible because node 2 and node 3, they are joined by an ideal voltage source. There is no series resistance connected with the source. There is no series impedance connected with the source, as if these two sources are connected through a voltage source, through an ideal voltage source. Then what we can do? Then we can combine those two nodes to form a single node as if, and we can write the KCL equation for that node. Am I clear? So when two nodes are connected by a voltage source, then those two nodes may be combined to form a super node. We can write KCL equation for that supernode. All right. Basically, Kirchhoff's current law we write for a single node, but that is not that limited. KCL may be written for a part of the circuit, as if here we have written the KCL for this part of the circuit, node 2 and 3 joining as a single node. Sometimes you see that more than two nodes also may be joined together, be considered to be a single node. If there is another node connected to node 3, say, by a voltage source, ideal voltage source, say to some node 5, then you can consider that node also as the part of the supernode. That means Kirchhoff's current law, it is valid not only for a single node, not only for a single point of the node of the circuit, it is valid for a zone of the circuit. Well, that means total current entering into a zone must be equal to total current leaving the zone of the network. Okay, this is the final form you can say. That means total current entering into a node must be equal to the current leaving the node, or the resultant current of a node is zero. Or this we can state in a different way: resultant current of a zone of the network is always zero. Okay, in that case, that zone means considering this part, node 2 and node 3. That means resultant current of this 2 and 3 has to be equal to 0. Okay, this zone may be expanded depending upon the connection of the circuit. If there are more nodes joined in such fashion where they are connected through ideal voltage sources, then you can combine them to write a single nodal equation, single KCL equation. Am I clear? Now, if you do this, you can, what is the expression say? This expression is now combining node 2 and node 3. Here, V1 is known, V2, V3 are unknown. Single equation, two unknown. So can you solve it? It appears that it cannot be solved, but you can solve. Why you can solve? Because V1 is already known, 50 volt, and V3 you can write in terms of V2. What is V3? V3 is, you say, it is V2 plus 10 IP. Okay, V2, then this rise in voltage is equal to V3. Okay, so V3 equal to V2 plus 10 I5. Okay, I5. What is I5? I5 is V2 minus 50 by 5. So everything is known. So V3 can be represented in terms of V2, means only V2 remains unknown. Everything is known except V2. So from the single equation, you can find the value of V2, which is 60. Okay, is it clear? Now see and tell me whether you could understand or not.
এখানে স্যার ওই মানে ওখানে এখানে যে ডিপেন্ডেন্ট সোর্সটা আছে, তো ওটার ইউনিট তো এখানে হচ্ছে অ্যাম্পিয়ার হচ্ছে, তো মানে
ডিপেন্ডেন্ট সোর্স এটা ভোল্টেজ সোর্স তো
হ্যাঁ
এটা কারেন্টের শুধু ভ্যালু অ্যাম্পিয়ার নয়,
তো
এটা কারেন্টের এখানকার বেলায় কি হবে 10 i5 i5 obviously is a current but
রেজিস্টার
obviously 10 i5 is a voltage. Okay, 10 i5 is voltage because it's a voltage source, so obviously is volts, so 10 i5 is a voltage, i5 obviously is a current, certainly a current, but 10 i5 is a voltage. Okay,
10টা তাহলে এখানে মানে হচ্ছে
10 as if
রেজিস্টার।
it is an impedance value, it is a resistor.
ওকে
Okay,
ওকে
একজনই কি সব প্রশ্ন করছো নাকি অন্যজনও করছো? আচ্ছা, এই প্রশ্ন করার আগে একটু নাম বলবে তো, আমি নামটা শুনি কে কে করছো। এনি আদার কোশ্চেন এনিবডি? এই প্রশ্নটা কে করলে? না হু মেড দ্য কোশ্চেন? নাম বলো। হু হ্যাজ মেড দিস কোশ্চেন? কে প্রশ্ন করেছিলে?
দেবার্ঘনন্দী।
দেবার্ঘ, হ্যাঁ। অন্য কেউ প্রশ্ন করো? আর কারো প্রশ্ন নেই? দেবার্ঘ ছাড়া আর কারো প্রশ্ন নেই?
স্যার হ্যালো।
হ্যাঁ বলো।
স্যার বলছি নোড 2 আর 3 এর মধ্যে যদি রেজিস্টার থাকে প্যারালালে কানেক্ট হয়ে, তাহলে কি ওটা সুপার নোড হবে?
না, নোড 2 হ্যাঁ, তোমার নামটা বলো আগে।
গালিব।
হ্যাঁ, নোড 2 আর 3 এর মধ্যে যদি রেজিস্ট্যান্স থাকে তাহলে কি হবে? তাহলে সেই রেজিস্ট্যান্স দিয়ে তো কারেন্ট ফ্লো করতে পারবে, তখন আর এটা লিখতে পারবে না। ওকে, অলরাইট। The two nodes are to be connected through ideal voltage source, then only you can form those two nodes as supernode. বুঝতে পেরেছো?
হ্যাঁ স্যার।
আর কেউ?
Sir,
বলো, নাম বলো।
sir Danish.
দানিশ, হ্যাঁ বলো। ওকে
Sir, why, sir, here you told that in 10 I5, 10 is assumed to be a resistor value. So why can't we replace it with a resistor and solve the circuit?
No. Actually, it is given that we have a basically this is a voltage source, dependent voltage source. How dependent voltage source appear in a circuit? Because of current flow, what happening is that when current I5 is flowing through this branch, automatically the source here depends upon this current, so that this voltage appears across that source. Okay.
Okay. Yes, sir, yes.
When
Okay, sir.
I5 current flows through this branch, then the source here, a voltage in this source will be developed, and that voltage depends upon this current. What is the dependence? Dependence is 10 times of this
Yes, sir.
current
Okay,
value.
sir.
Okay.
Like I5 will change, then the value of voltage source will also change.
If a value of I5 changes, value of this voltage also will change.
Okay, sir. Thank you,
Okay,
sir.
that's why it is dependent source. Dependent on, it is the
I5
current controlled voltage source, dependent on
voltage source.
some branch current. Okay.
Okay, sir. Okay,
Voltage
sir.
source, but dependent on some branch current.
Okay, sir.
Any other question from anybody else? বা যারা প্রশ্ন করেছো তারা যদি আরো কিছু না বোঝো জিজ্ঞেস করো। ওকে, then it means that everybody could understand, all of you could understand. আর কোনো প্রশ্ন নেই? anybody? Okay, then if there is no other question, then let us move to the next case, the figure 12. Now we shall consider the case of a super mesh. Super mesh, as I told you, is nothing but a mesh including more than one mesh. Okay, more than one mesh is appearing as a single mesh, is being considered as a single mesh. Then this larger mesh is called a super mesh. Sometimes we shall have to consider this type of meshes. Okay, so figure page number 12 and figure number is F12.1. Okay, figure number is given same as the page number and then 0.1, 0.2 for different figures. Okay, here we have a very simple circuit again. simple resistive circuits, okay, and voltage source 100 volt here, 5 ampere current source, and then again voltage source of 50 volt. Okay, now distinctly you see that actually the name of the nodes are not given. It would have been better to explain, easier to explain if had we given the name of the node. Okay, you can write some name, okay, for this node. Okay, so you should now visibly there are 3 nodes, 1, 2, 3. কারো একজনের একটি মাইক্রোফোন খোলা আছে, তোমরা সেটাকে নয়েজ আসছে তো, যখন প্রশ্ন না থাকবে তখন এটা অফ করে দেবে, and when you make question then you on it. Okay, turn it on. So now you see that there are 3 distinct nodes. We can see this is loop. Okay, very simple circuit. Loops are detectable and they are visible, very simple. IA is the loop current in this loop, say loop A. IB is the loop current in loop B, and say IC is the loop current in loop C. Okay, now can you write the expression or can you write KVL equation for loop A or loop B or loop C? Sorry, for loop B you can write the KVL expression. What is that? It is 10 IB plus 2 into IB minus IC plus 3 IB minus IA equal to 0. It is very simple. You can write this equation. Okay, but for loop A or loop C, can you write the KVL equation? Can you write?
নো স্যার, এর কারণ মানে ওখানে ওখানে যদি কারেন্ট সোর্স আছে তো ওটাকে আমাকে ভোল্টেজ সোর্সে কনভার্ট করতে হবে, তো এই জন্য এখানে একটা একটা যে কমন ভোল্টেজ করে নেবো, তো যে তারপরে ওই দুটো লুপ মানে একটা লুপ হয়ে যাবে আর কি
লাস্টলি একটা লুপ হয়ে যাবে, অর্থাৎ তুমি সরাসরি you cannot directly write the loop equation because you don't know the voltage across the current source. Okay, কিন্তু আমাকে ভোল্টেজ ইকুয়েশনই লিখতে হবে. I cannot write in terms of current values. Okay, therefore what we can write, let us first, to show how that can be done, let us first consider that across the source the voltage that will appear is equal to V with a positive polarity here at this junction 2 ohm and the current source junction, and negative polarity at the junction of 6 ohm, 4 ohm and then negative terminal of the current source. আমরা এখানে positive terminal দিলাম কেন? Because arrowhead of the current source is at the positive terminal and the other end is at the negative terminal. So accordingly say V is the voltage across the current source. আমি যদি V voltage ধরে নিই, now I can write the loop equation. It is 100 equal to 3 IA plus minus IB plus V. Okay, আমি plus লিখছি কেন? Because in the direction of current I am assuming writing the voltage to be positive. In the direction of current কি হয়? There is a drop in potential. So drop in potential I am giving a positive sign. So that's why 3 IA minus IB is considered to be positive plus from positive to negative terminal of this voltage, that's why plus, then 6 IA plus 6 IA equal to 100 volt. This is for loop A. And for loop C, what you can write? It is 2 IC minus IB, 2 IC minus IB. Then it is minus 50 is the source here. Then 4 IC minus V. Then plus 2 IC minus IB equal to minus 50 volt. Okay, because it is in the opposite direction, so it will be minus 50 volt. So 2 equations, one for loop A, one for loop C, have been written. Now what you can do, we can combine these 2 loops to replace V. To replace V, you can combine these 2. You are getting this total. What you are getting, 50 equal to, adding these 2, that is 100 minus 50 is 50 equal to, then 9 IA. 9 IA means 3 IA plus 6 IA is 9 IA minus 5 IB, minus 5 IB because it is minus 3 IB and here minus 2 IB, minus 5 IB plus 6 IC. 6 IC because 2 IC here and 4 IC here, plus 6 IC plus V and minus V cancels out. Okay, that means we are getting this equation. Combining the top two equations, we are getting this equation. Okay, we can rearrange. This is the equation, therefore, and separately we can write the equation for B. That is very easy. For equation for loop B, you can write the equation, but for loop A and loop B, we have written two equations. Then combine those two equations to replace the unknown variable V, that means the voltage across the current source. We have removed this and written this equation. And now you see, if you see this equation 1, you see that this is nothing but the equation for these two loops together. In this loop, IA is flowing, in this loop, IC is flowing, but while writing the loop equation, we have written the equation of this larger loop. In this larger loop, actually, there are two loops, IA and IB included. Okay, that means this equation, this is nothing but an equation combined for two loops. So this is the super mesh equation. So, okay, that means a super mesh basically includes more than one mesh. Okay, more than one mesh. Sometimes there may be three meshes. Okay, depending upon the situation. So this is the equation. This is the equation. Here the variables are IA, IB, IC. Here also variables are IA, IB, IC. Two equations, three unknown. Appears to be that the equation this cannot be solved. But advantage now the situation is such that you see that basically IC minus IA equal to 5 ampere. 5 ampere is the current source value from this node to this node, and IC is the current in this loop, IA is the current in this loop. This IC and IA, they are in the opposite direction. Direction of IC is same as 5 ampere, so IC minus IA is actually equal to 5. Then from here we get a relation between IC and IB. We may use this relation as an equation. Okay.
স্যার বলছি যে ফার্স্ট লুপে এ লুপে আই এর কারেন্টটা যে ক্লকওয়াইজ ডিরেকশনে রয়েছে, কিন্তু ভি এর ভিটা তো যে প্লাস, ওটা তো অ্যান্টি ক্লকওয়াইজ ডাইরেকশন আছে, তো ভিটা তো নেগেটিভ হওয়া উচিত। যেখানে
কোনটা
ফার্স্ট ইকুয়েশনে ফর এ যেটা আছে, ভি এর সাইনটা কেন প্লাস হলো সেটা মানে বুঝতে পারলাম না অ্যাকচুয়ালি
এই ইকুয়েশনে।
না উপরেরটা ফর এ যেটা ফার্স্ট ইকুয়েশনটা,
হ্যাঁ
সেখানে
কেন পজিটিভ হচ্ছে বুঝতে পারোনি তো? আচ্ছা দেখো, ঠিক আছে, আমরা সাধারণভাবে কি হয়,
প্লাস দেওয়া আছে, প্লাস থেকে মাইনাস তো অ্যান্টি ক্লকওয়াইজ হচ্ছে সেই জন্য।
না এখানে অন্যভাবে, হ্যাঁ আমি বলছি তবে বেসিক্যালি কি হয়, আমি যখন ইকুয়েশন লিখছি তাহলে জেনারেলি হোয়াট ইউ কনসিডার, আমাকে একটা কনভেনশন ফলো করতে হবে। হোয়াট কনভেনশন আই হ্যাভ ফলোড ইন রাইটিং?
কারেন্টের ডাইরেকশনটা যেটা হবে সেটাকেই কনভেনশনাল ডাইরেকশন ধরতে হবে, মানে ক্লকওয়াইজ যেটা।
তাহলে এখানে আমি কি লিখলাম, 3IA minus IB। 3IA minus IB আমি যখন লিখলাম, কারেন্ট ইজ ফ্লোয়িং ইন দিস ডিরেকশন, তাই তো? কারেন্ট ইজ ফ্লোয়িং ইন দিস ডিরেকশন। তাহলে এই ডিরেকশনে যখন কারেন্ট ফ্লো করছে, তাহলে 3IA minus IB এটা একটা ভোল্টেজ ড্রপ। অবশ্যই কারেন্ট ফ্লো করছে ফ্রম হায়ার পোটেনশিয়াল টু লোয়ার পোটেনশিয়াল। সো while moving to higher, from higher to lower potential, I have given a positive sign. When drop in potential has been given a positive sign. Is it clear?
Yes.
Now here, this terminal is positive, this terminal is negative. এখানে ভোল্টেজটা কত, এটা আই এর উপর ডিপেন্ড করছে না। এই ভোল্টেজটা হচ্ছে ভি, আমরা ধরে নিয়েছি ভি। কিরকম ভি? উইথ এ পজিটিভ, উইথ এ, দ্যাট মিনস হিয়ার ইট ইজ হায়ার পোটেনশিয়াল, হিয়ার it is lower potential. So while we move from here to here, I actually am moving from a higher potential to a lower potential. Right? Same convention I have followed. That means here higher to lower potential is considered to be positive. Here also higher to lower potential is positive. Here also 6IA higher to lower potential movement is considered to be positive. Is it clear?
Yes, sir. Okay.
Okay. Now you see that these two equations, similarly the second equation has been written for loop C. Now combining these two equations, I have written this equation. Now in this equation you can see this equation as if we have written a single equation including both the loops. Okay, So we have considered this drop in terms of IAIB, this drop in terms of ICIB, this drop due to voltage source, then this drop due to 4IC, then this drop due to 6IA, and then this voltage source. Okay, so this outer loop we have considered. In this loop, it is actually enclosing two separate meshes. That's why it is called super mesh. So this is a mesh, this is a mesh, but this outer mesh is the super mesh because it is enclosing two meshes. Okay, and we have written equation for that. So sometimes you may have to write, for simplifying analysis, you will be writing mesh equation including more than two meshes. You will be writing nodal equation considering more than two nodes or more than one nodes to be behaving as a single node. So when we do that, then it is the super node. When we include more than two meshes in a single mesh, then it is the super mesh. Is it clear how we define and how to handle this type of situation when you have encountered super loop or super node? Okay. Is it clear? Any question after this?
Yes, sir.
Sir, can you
Okay.
repeat the previous statement once more?
Statement is that when more than one nodes are considered as a single node, and we write KCL equation for that, then that nodes combined node may be considered as a super node. That means in super node we have more than one nodes included, and we can write a single equation to represent more than one node. Okay. In super mesh, we basically include more than one mesh to write the KVL equation. That means when more than one meshes are included in a single mesh, that larger mesh is called the super mesh. When more than two nodes are combined together as a single node, then those nodes together is called the super node. Is it clear?
Yes, sir.
So these are the expression. Now again in page 13, you see that again we are considering more equations. So now I shall not proceed any further today. We will stop at page 12, and I shall ask you to go through these pages. Okay, the example shown in page 13 and also in 14. Okay, again these are the examples of super node and super mesh. You see this, I shall explain this in the next class, so that will be helpful for you. So you first study this, go through these pages, page 13 and 14. There are more examples. Simply extension of today's discussion is there. Okay, applied to two different circuits. Okay, maybe somewhat more complicated. See
Sir,
whether bolo.
sir, in page number 6, sir, in your notes, sir, in page number 6, will we call it a super mesh, sir? Because there is a
Page number 6.
yes, sir.
Page number 6. বেসিক্যালি আমি কি করতে পারতাম, আমরা কি করছি as if এইটাকে আমরা লিখছিলাম, তো ইট ইজ এ কারেন্ট সোর্স। ওকে, এটাকে সুপার মেশ হিসেবে লেখা যেতেই পারে, বুঝতে পেরেছো তো? এটা আমি সুপার মেশ লিখতে পারি, কিন্তু আমি এখানে কি করেছি, আমরা এটাকে চেঞ্জ করে নিয়ে আলটিমেটলি কারেন্ট ভোল্টেজ সোর্সে চেঞ্জ করে নিয়ে ইকুয়েশন লিখেছি, সুপার মেশ হিসেবে আর রাখিনি। কিন্তু আমি চাইলে সুপার মেশ হিসেবে লিখতে পারতাম। I could write equation in that way, but we have not introduced that at that point because we have not explained it. Okay, but we could write in form of super mesh.
Okay, sir.
So you can try it, and if any problem, if you face any problem, you state in the mention it in the next class. We shall explain. All right.
Okay,
sir. Up to page 12, I have discussed. Next day, I shall discuss page 13 and 14. If you go through these pages, then very rapidly I shall be able to complete those 2 pages, because you have already seen. But if you face any problem in understanding, obviously I shall discuss in the next class. Okay. So everybody should go through page 13 and 14, where more examples of supermesh and supermesh are given. All right. Okay.
Sir, can you provide us with the recorded video lectures of previous class and this class?
All right. All right. So I can send you. And now next class will be as settled. Every week we shall actually have two classes, Tuesday and
Friday.
Friday. Tuesday 4:30 and Friday 4:30. Sometimes, if required, if it becomes difficult for you or difficult for me, some adjustment, say half an hour advance, it will be done. Okay. But generally, we shall start at 4:30. I shall send you the link. So I shall send you the recording also. No problem. Now today, some of any one of you call the name and
Yes, sir.
others
I am
respond.
calling.
Coach.
Roll number 87.
Present.
Roll number 88.
Yes, sir.
Roll number 89. Roll number 91. Roll number 92. 92. 93.
93 present.
96. 97. 98. 99.
Yes, sir.
100.
Yes, sir.
101.
Present.
102. 102. 103.
Yes.
104. 105.
Present.
111. 112. 112. 114. 116. 118.
Present.
117. 119.
Yes, sir.
120. 121.
Present.
122. 124. 124. 125. 125.
Present.
126. 127.
Yes, please.
128.
Present.
129. 130. 131.
Present.
132.
Present.
135.
Present.
136.
Present.
138.
Present.
139. 140.
Present.
141.
Present.
142. 142. 143.
Present.
144.
Present.
145.